Hi and welcome. Now we're on episode 11. We are just about to figure out why Simplified Transitions is mangling my transitions for the string state. So to figure that out, what I want to look at is my state, pretty name, and I want to keep going through these until I see that I am looking at the string state. I would like to be able to use a conditional breakpoint here, but writing a conditional breakpoint that does string compares is a little bit annoying. Here it is. Okay. Alright, so I'm looking at the first transition here. Here's my condition set. This text might be pretty small. Let me see what I can do. I'm not sure if I can make the table text any more readable over here. I mean, it's kind of too small for me too, but I actually don't know how to even make Visual Studio make it bigger. Let me take a quick recess to look that up. Visual Studio table text size. Debugger table text size. What are you talking about? Alright, giving up on it. I can't seem to find anything that straightforwardly states what I'm looking for, so tiny little text it is. So we look at the condition set. So this does actually have a pin, which is what we expect, and one input. That pin there looks like this. Flag value 0. Okay. So if we see a quote and the char flag is 0, basically. We put that out. Very good. Here's the second one. We get the condition set. This condition set looks similar. It has one input. That input is different now. It's the single quote. Right? So I'm going to double check that. Yep, that's the single quote, and we're saying that the char flag should be 1. Now I'm going to do a set subtract, and this is where things must be going wrong, I think. So I have one node from each. They're going to have to do a subtract here. So let's see how this goes. A minus B input is 1. So if the count is 0, no, it's not. If the count is equal to the A input, it is. So then the new node has that fields That's weird. So A minus B was empty, and we're outputting the fields B? I think that's wrong. Let's take a quick look at the logic for this again. So this is line 1017 of the main file. And let's look at our notes over here about subtraction. So subtracting two nodes from each other has these possible formats. Let me rename these because I remember last time this being a little bit confusing. This is going to be called A input and A field, right? So, whoops, you stay where you were. So one at a time here, I'll go D is B F, C is B I, B is A F, and A space. Wait, that's bad already. Why do I already have BF everywhere? Okay, let's do this in the other order. A is AI, B is AF, C is BI, D is BF. There we go. Alright, so now A minus B input, so AI minus BI is the empty set, which means we're looking at this case here. Or A minus B is the opposite of the empty set. A minus B is the full set. That makes this the empty set. Okay, so if this is an empty set, why don't I just go through the whole thing? So if A minus B, if AI minus BI is the empty set, then we take a copy of A's inputs and the difference of the A and B fields, and that's our new node. If this is the full set, that means this is the empty set, and so we can do A minus B, which is the same as the full set, but doesn't matter, cross with the A fields. If the A minus B fields are the empty set, then we can take the A minus B input crossed with the A fields again. So AF minus BF is the empty set, yields this. Okay, so that might be the source of some of the bugs. Let's take a look now. State string. So now we have, if we have a quote and this is a 0, we emit a string literal character. If we see a single quote and this is a 1, we do a different emit for a character literal. If we see a slash, then we go to the string escape thing. Yeah. If we see what is this? If we see a new line character, we emit a Lexer error and we go to the root. If we see either of these in the flipped cases, we stay here and go to, we just stay here on the string and ignore it. We're still missing the fallback at the end. You see that? So at the very end of string, there's a fallback back to string, and it's not showing up here, but it should. It should show up as another transition. Okay. So I want to take a look at that again in the debugger. Just same thing we did before. Yeah, a little too zoomed in there, at least for me. Looking for the string state again. There it is. Right. Okay. So going through here, this starts working and it's all good. So 1, 2. I want to see, before we go too far, what are the transitions this thing even believes in? It believes in 7 transitions. So we've done 1 of them, 2 of them. I want to keep an eye on what the transition we're looking at looks like. It's almost the exact same timing as the sneeze on the previous episode. It's crazy town. Anyway, I gotta readjust myself after that. Threw my spine out of the whack sneezing that hard. Give myself a headache. A little coffee will help. Okay. So, we are looking at these 7 transitions. The transition we're on, we want to know what it looks like. So the condition set we're on has fields that it's interested in and inputs that it's interested in. Okay. And I just want to skip through there. So here we are again, still caring about a particular flag. I think we've done 2 now. Right? Are we caring about a particular flag? No, this one doesn't care about a flag. Okay, so that's how far I need to expand it to see. This tells me if I have any lists. If I have an empty list here, then it's the full set. So now I'm on the full set, and I have 1 input, and that 1 input is the new line character. So this is the one that emits an error. Here we have a flag again, so I think this must be, if it's 34, I think that's a quote. Yes. Okay. 39, I think that's a single quote. Yes. So, how many of these have we done now? We did... Oof, I don't have a counter anywhere. Quote, tick mark, new line character, backslash, quote, tick mark. So that should be 6 of them. I want to see what happens after this, because there should still be a handler. 3, 4, 5. So there we go. We just checked 5 things. We still have a good condition set, so we have 1 more. What does this one look like? So this has 257 possible inputs, and so this is our fallback right here. Right, 257 inputs, the entire range of possible fields. What happens to this when we try to simplify it? So we're going to do a loop that repeatedly shrinks the set down and down and down by taking out things that have already been ruled out. And this is going to become a fairly complex representation of a set as it goes, because it started off as the full set, so it has no pins and all possible characters. And then it's not just going to have some characters removed or a couple of pins added for it to cut out possible flag states, but it's going to have specific things removed. So it's going to, for instance, go in there and remove a particular character, like the quote character, but only when the particular pin is set. So they're not, the set will have to split itself into, sometimes the quote character is caught by the fallback, but only when this pin is set, and other times the quote character is not set, and that's when this other pin is set. Does that make sense? It'll have to start bifurcating the set into what happens if this pin is 0, what happens if this pin, if this flag is 0, what happens if the flag is 1, and then as it goes, it might like get complicated and then simplify itself and get complicated again and then land in a particular state that we'll discover as we iterate it. So we have to do the partial here. So this is taking node A minus node B. Node A is going to just be all possible inputs and all possible flags. Node B is one pin, so the car flag is pinned to 0 if I remember correctly, and one input. What happens? Well, this is 256, so it's not 0, but it's also not full. We do the subtract. So field set subtract fields A minus fields B. We look at the list of the field set A. We do subtract this. Okay, so A minus everything in this list, I think. Growing list. Let's see what happens. Yeah. Next list equals 0. Pin equals list first. So the first pin we look at says, okay, here's a local pin. We're going to push that onto the growing list. So the growing list now contains one pin, and that has the flag and field, the flag pointer and the flag value that were copied out of pin, right? So 40C 480 and 0, and local pin 40C 480 and 0. Then we call this again, and now list is 0, so the question is, do we have any conflicts? So the way we find out if we have any conflicts is we're copying the A pin list, which is just a list that contains nothing in it, so that it represents the full set of possible pin flag states. And then we're saying, are there any conflicts? So that will just skip this part of the loop entirely. There are no duplicates, no conflicts, everything's good. We copy the pin from the growing list to make a non-local, because this was just a local pin here. We make a copy of it that's actually on heap memory, right? Stable memory. We flip the field, so this becomes a 1. And so now we have 40C 480 and 1. The reason we flip that is because when we're subtracting these things, if we are subtracting all the states where the flag is 0, then what we have left over are all the states where the flag is 1, right? We push that onto the new list. We go check the next flag in the local copy of the list, and we're done. We have no more next flags. Found no conflicts along the way, so we take the new list and we push it onto our result. Now our result is just a field set, right? So it's just a list of these field pin lists. Boom, boom, boom. And so out the other end we have this thing here, which is now a simple list with one pin in it that pins a flag to a 1. So there's our partial. Then what we have to do is, this thing is just a partial of the whole thing we want. We next look to see if like how to concatenate that to the whole thing, and that's how we do it in this case. So now our result is just that. Okay. Alright, so A minus B fields. Looks like that. And so it's not empty either. Okay, so we're now in the situation where I think this is correct, that looks good, and this looks correct. It's 1 less than 257, so when we did A minus B on the inputs, we got all of the inputs except the one that got removed, left over, right? So A minus B input is fine. A minus B fields is fine. So now we take A intersect B and we get just the 1. And that's the quote character. And we're saying we need 2 different nodes. One of the nodes is A int B, so that thing, and the fields A minus B. So let me double check our logic over here that makes sense. So the intersection of AI and BI and the subtraction of AF and BF, yeah. That's what our math says anyway. We take the node 1 and we save it. We take node 2. Node 2 is A input minus B input times the A fields. So we, see, that's copying the B fields. That should really be copying the A fields. Right. Okay. What are you doing? Is this because caps lock is on? That explains it. It's not just that though, it's acting like I don't know what's going on here. Something weird. But my character insertion isn't working at all. Okay, I need to save and close. Close, close. It won't let me close. Maybe if I did this. No, it doesn't work either. That was bizarre. Something weird's been going on with 4coder all day, but that was particularly unusual. I've literally never seen anything like this. So I'm a little bit... It's not just that though, it's like my whole computer is acting strange. I can't... Is there like... one of these keys is stuck or something? I can't even type. It's acting like a control key is being pressed somewhere. There we go. Okay, I must have had a control key that was just slightly pressed and it was sticky or something. Never had something like that. That's weird. Okay, well luckily it's over. I can type into my browser again. Thank goodness it wasn't a 4coder bug, because then that would have meant that I could have been inflicting that confusion on other people, and I think it was just my keyboard key got stuck a little bit, like just barely pressed enough that it was registered as holding control down, but it didn't look like it was stuck or anything. But yeah, there we go. That's unfortunate because it does mean we lost the set math that I had worked out. Okay. Alright, even now we still don't have the fallback state actually showing up. We have 1, 2, 3, 4, 5, 6, and there are supposed to be 7. The last one's supposed to be the fallback. So we're still not there. Let me just double check that the print looks correct again. 'Cause the fact that we're only not showing the last one is just slightly weird, it seems like. Trans does not equal 0. Trans next. I don't know. Looks right. First, last, transition. Yeah, that seems fine. I mean, a lot of these other ones, like this, didn't lose its fallback or something. So I think this really is a matter, like this fallback looks like it subtracted this one thing out. Right? This fallback definitely subtracted two things out successfully. So I think this is just a failure of the set math still in this case, where there are like complicated flag relations happening. Because there's like There's definitely weird stuff where it's gonna like first it's gonna complicate because this gets subtracted and this gets subtracted, so it's gonna end up in like 3 or 4 separate nodes. And then when these get subtracted, it kind of balances things back out because it'll actually turn out that we fully subtract the quote character, but you don't know that until you see this and this, right? So I guess there's actually one way I could have thought about this problem that I didn't consider in the past. I'm not sure if it's worth it to change to this now, but it might have been easier to get the code right if I had done it this way, which is very often when there's a flag pin, it's going to be reversed somewhere else in the set, and even in the state, and even if it's not, we could simplify things by saying for each character, fallback says I operate on all the characters, so just say for each character, as an iteration of 257 things, check to see this flag like conditions under which that thing can still be reached at the end. If there are none, so like here we would find out quote got fully subtracted, just take it out. It doesn't go out. It doesn't go as part of this fallback. Same thing would happen here, and then our fallback should actually just end up with all stars covering everything, and then 1, 2, 3, 4 things subtracted. That's how it should look. It should look like 253x all possible flag states, because we're actually just fully subtracting out quote, single quote, backslash, and the new line character, and then what should be left over is just something that looks kind of like this or this or this. But somewhere along the way, the number crunching on these, or the set crunching on these flag pins is complicating it to the point where it thinks it doesn't have a set left over or something. So I still need to walk through this and figure out what's happening. We're finding bugs, but we're not finding enough bugs to make it work yet. And maybe if I had done this like as looking at things from the perspective of one character at a time, it would just organize things in a slightly simpler way. Even though it would be less performant, I think it would have been the easier way to organize the code. I still would have had to have flag pins though, and all the complexity that relates to, but I think I could have managed them more simply too. Here it is, string. So we want to look at each of these, so show me the transition we're looking at. We're looking specifically for the transition that is the fallback transition. So condition set, first input, we want to see when this one goes up to 257, or 257 possible inputs, right? There it is. Alright, so the first subtraction happens. Does this come through? I don't know. Condition set, what does that look like now? The condition set now has 2 nodes. The first node has 1 possible input, the quote, and 1 possible flag, or one flag pin which pins the char flag to 1. So we can see the quote if we have that flag set to 1, and then what does the last node, the second node I should say, look like? Well, it's the other 256 inputs with no flag pins. That's what I would expect in that situation. What about this? Now we, for the first time ever, are looking at a condition set with 2 nodes subtracted from another condition set, and this condition set again is kind of going to poke a hole in a way that requires it to split into more nodes. So we'll look at each node. The first node here is the node that represents the quote character, and when we do that, we're going to get an empty set here, right? A minus B, no, this is A minus B, so we're going to get a full set. And so it goes, aha, full set, A minus B is the full set, so we put inputs there and keep the original flags the way they were, no change, and there we go. So that node is done. We have a partial with 1 node in it, and that 1 node is the node that was already in the original condition set A, and we set our result to look like that. Okay, so we have that first node, it's preserved. We go to the second node. So the second node is the one that has 256 inputs, and no flag pins. And now we're going to do something very similar to the first thing we did, which is it's going to end up having to split it into 2 nodes again. And we think this works, so I'm going to just come over here and say, okay, let's look at each of these. So the first node that we output has one possible input, the single quote, and it has a flag pin that pins the char flag to 0, right? The second one has 255 inputs remaining, and it allows all possible flags. So we're allowing all possible inputs bar 2 under every flag condition, and then we have a special node that represents the quote character when the char flag is set to 0, or set to 0, and another one when the so the string character when the char flag is set to 0, and the wait, let me double check that I'm saying this the right way around. So when the char flag is set to 1, right? When the char flag is set to 1, the string character still gets called by the fallback so far. And when the char flag is set to 0, the char character, the char delimiter, the single quote, is still a part of the fallback, at least so far. Later, those nodes should get removed when they get subtracted out by later stages. So what's kind of interesting is node sub doesn't seem to have any way to represent the possibility that it returns an empty node entirely. That might be the source of our problem. There might need to be a way to say, hey, result set comes back with no nodes in it, right? In case this node got completely turned into an empty set when it got subtracted by that node. And that's going to come fairly soon. So let's keep going through here. So set subtract worked for now. Condition set now has, it should have at least 3. Why does it say 1? Something went wrong just now. SMI condition set subtract. What happened there? Something happened in the combination of those second and third nodes to the first one. What did you do wrong up here? SMI condition set subtract. So we are trying to create the new one here. There's only one B node, so there's no shenanigans happening there. It's all this. If partial.first does not equal 0. Duh. Okay, so if partial first is not 0, do I have other places where I do that? Partial.first equals 0. Okay, so I just messed up right there. So the point is, if we get back an empty partial here, we want to do nothing when we're considering expanding the result. If the result is also already empty, we don't care about this. But if partial is empty, but result was not, leave result the way it is. If they're both not empty, then join them. So now we actually want to do a quick moment of math, set math. In particular, how do we determine when this will turn out to be the empty set? So again, we're doing AI x AF minus BI x BF, and the equations for that basically work out to be if AI originally included 1 and 2, and AF originally included A and B, and then BF takes away 1A, then what's left over is like this, right? And so you end up splitting it in one of two ways, this way or this way. So if you're splitting it this way, you need 2 nodes. The first node is everything, so the number part is everything subtracted like this, crossed with everything that was not subtracted was subtracted minus everything that was not crossed with everything that was not subtracted, union with okay, numbers, everything that was subtracted, or everything that was not subtracted, crossed with everything altogether, right? So AF takes A and B, A and B crossed with everything that was not subtracted, right? When we do A minus B, the thing we have left over is anything that was not subtracted, which is confusing for some reason. The leftover. We want the leftover, which we find by taking the subtraction, which is 2. Union that with the things that were subtracted, which is the intersection, crossed with the flags that, the letters that were left over. The other way to split it is like this. This time, we are going to do, one of the clauses is going to have everything that was left over when we did the flag subtract. So the flag subtract, yeah, that's this part. So AF minus BF gives us every B, and we want to cross that with AI, all of the inputs that that A ever had. So that is B, because the things that, the leftover from AF minus BF crossed with all of those, union with the things that, this is right, the numbers that were subtracted This can't be right. Oh, that's the flags that were subtracted. The flags that were subtracted and the numbers that were left over. Alright? So this is A was subtracted, so that's a flag. The flags that were subtracted crossed with, oops, what did I do that for? Should be like this. So crossed with, well, it can't be everything. It's got to be a subtraction, right? That's what. Okay. Subtract with whatever's left over when you take away the numbers that B takes away. So we have 1 and 2. We take away 1. 2's left over, crossed with the things that were subtracted, which are A. Right? So those are the two equations. Now this will be the empty set. I think if and only if this and this are both empty sets, right? In other words, if when we go to do this, what has to happen is AI minus BI is completely empty, thereby meaning that all of the numbers are covered, and AF minus BF is completely empty, thereby meaning all of the flags are completely covered. That would be essentially saying that A is equal to or is a subset of B in every dimension, right? That's what it is. So, when we're over here, there's another case. If, oh, we already handle it, because this is checking if count is greater than 0, so we do A minus B fields. If that's greater than 0, we put it in. If it's not greater than 0, we get the empty set. Okay, I actually already can't handle that. We're fine. All right, so let's keep pressing forward then. I think now's a good time to check to see how we're doing with state string. Ah, here it is, just like I said. So you can see that this cancels with this and this, and we end up with just all of the quote and single quotes completely removed and a simple flag statement there. So are there any other cases where the flag statement does get complicated? No, there aren't. So that looks good. I do want to keep on doing some things to check some stuff. So all of these should always have a situation that like has a fallback or that some kind of guarantee that everything is covered. So like I just want to do a quick perusal from bottom to top that everything in here covers every possible input. So that looks like good. Let's see, dot and star removed, so that looks good. This is saying consume everything I see. or don't consume anything ever, do an emit, and go to root. So this is an example of a state that will hopefully get optimized out, right? Because this emit, go to root will get pulled up into some other, or rather, this emit will get done, but then this go to root will be splayed out into a bunch of other things, and those bunch of other things would hopefully be things you could drop down to, like, multiple different things would have to do the same thing. There is a question here about how I would optimize this, in the sense that this emit here is a bit weird, because that emit might be that there are other op stages that also have the same pattern, but they emit something different. In which case, what I might need to do is think about saying, if these are going to emit no matter what, then maybe an emit that comes first wants to get transferred to the other side before the go-to, right? So whoever's trying to go to this op stage is doing like okay, I consume my input, and then this thing here is saying, okay, no matter what I see, I emit and I go to root. Well, why isn't that emit just living right after this consume then, right? That's kind of the idea that I think would make some more sense. Like here, we can see that what this is really doing is saying, if the next character is a pound, consume it and emit a particular thing by going to this stage. If it's not a pound, then emit something different and go to root. Well, really what we should have here is something that's basically like, if the next thing is a pound, consume it and emit this thing. If it's not a pound, then first emit and then consume the next character the way root would, if we're going to do a table lookup acceleration. If we're going to do control flow acceleration, we might want to do this a little differently, because go to root would end up kind of expanding the size of the code quite a bit. Anywhere where we try to go to root from emit, it might make more sense to have a jump that's like the universal handler for this, so that you can have different types of emits that then all do the next follow-up the same way. We'll see about that. We'll see about that. But we have options. So anyway, scanning through here for now to find the, you can see there's a lot of these op stage things, and the reason there are so many of them is this is the automatically generated operator parser. So it's doing things like checking these, and these things at the end are all just things that all basically say, I already know what type I need to emit, and I'm just saying whatever character you see, emit it and go to root. And so that's like a pattern that if I find a way to optimize the no matter what, emit a particular thing and go to root, if I optimize this, then this stuff can simplify a lot, right? Okay, what else we got here? Yep, you're covering. Just looking to see if there are any lists of transitions that don't look like they're covering their bases. 236, so the reason that number is so small is because this is the root, I think, of a long chain of, yeah, this is an operator parser root, so you can see it's like, there's a lot of characters that can begin this operator parse, right? And so, yeah, okay, I was just checking something that was a little confusing. So all of these individual characters get subtracted out of our fallback, and we end up with 236 characters remaining, which is kind of cool that we know that now, right? We know what set of characters it is. It's not just fallback, but we actually do know the set and the size of it and everything. Interestingly, here we also have, like, these look like they're repetitive, they're all going to op stage, but they're actually just, there are multiple states called op stage, since these are automatically generated states, they're not handwritten. And there's this other cool thing that happens here that we can see, some of them emit right away, so like certain characters are, have the property that when you see them, they immediately are a finished token. There is no continuation off of them. And so for them, we just consume, emit that character, emit the token, and go to root right away. But for others, we can see that like equal could be a token, but it matters what comes next. So that's where there starts being those things that's like, okay, the fallback for this state will say to emit this token here, but if the fallback is the only thing that exists, maybe that needs to be placed one step higher at the tree so that we can avoid having this stuff down here. Like, instead of putting these in this way, we should have, maybe when we generate the operator parser, just a thing that says, hey, if you were going to just be putting in one of these peak handlers at the end anyway, why don't you just say don't bother generating the state and stuff that as the where's an example? I mean, basically these are doing a thunk, in the other words. They're just doing a thunk that has an emit. So it might actually make sense, before we try to do a full state machine optimization, to do a pass that does, like, look, a lot of these are like clearly no ops in the sense of, at least in the state machine, and so all they contain is one state, or one transition rule that catches all possibilities, it does no consume, and it does some actions, and then it does a transition. Well, we should just say, whenever you see one of these, find all the people transitioning to that state, and replace the case that causes them to transition to here with the rule that says do an emit and then go to root instead of going to me, because that's what all I'm going to do, right? And that would just shrink down the set of states quite a bit and make the other optimization work cheaper. This is a fairly cheap thing to ask for, and it looks like we have a lot of these thunks actually from the generated code, plus a couple from the handwritten code. So that might be a worthwhile, like, first step before we do anything a little more hardcore. Comments. All 255 get caught there. Comment block new line. Go to comment block. So this is a thunker too. You can see that here I'm saying no matter what you see, go here. So this was clearly setting a flag or something. Comment block new line. Yeah, it's only getting mentioned right here, and the two flags being set there, I'll bet you, are probably being pulled in from here, and so this is just turned into a thunk now, a no-op state that we could just remove. Here's the delimiter match. I've kind of shied away from explaining it fully so far, but it shows up in one spot in the whole system, right here. Here it is trying to match that delimiter. If we keep going up, we'll also probably see the spot where it sets, yeah, mark one pass last, and somewhere in here there should be one. Raw string is actually a thunk now. And yeah, so anyone transitioning to raw string, which is actually only one spot, does the delim mark first that was actually conditioned on the state originally. And then the one pass last is stuck onto this transition here. And I bet you that this, yeah, this is also a no-op thunker thing. Although it looks like that actually isn't exactly a no-op because it consumes its input, but it will turn out that I think the one person who's calling that is not consuming their stuff. So what's really going to happen is this state is going to become unreachable when we pull things forward, not by any other method. It's just going to become unreachable. That's how that state will get removed. Okay, I need to keep making sure that I'm checking, by the way, for these fallbacks too. So you have a fallback, 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 you have a fallback. So all look pretty good. I think we're actually doing the right thing now. Here we can see spaces, slashes, and parentheses do something special on the raw string get delimiter. So when we're trying to do raw strings, these three things have special behaviors. Oh, if we see any of these, it's a Lexer error. None of these are allowed in a delimiter for a raw string. So, there might actually be others that aren't allowed. I bet like new line characters, bet no white space is allowed at all. But those are the three I have handwritten in so far. That's what those are. This is the end of a delimiter. Escape. So there are 22 different inputs that constitute a legal escape right here, and then 235 left over. So I think those 22 inputs are the 16 possible hexadecimal inputs, including upper and lowercase, right? 16 plus 6, yeah, that's what those are. Yep, so this is basically allowing for hexadecimal. You can see that there's this 8765 thing going on here. This is a case of where like a state machine isn't exactly the best way to represent this idea. What you really want is sort of like a counter, because you can either enter this at 8 or at 4, and then it counts down to keep track of how many you've had, and you can't have more than a certain number in the grammar of the Lexer. But adding actual counters into the state machine would complicate the optimization process a little bit, so I have a choice when I am writing the code between adding a new feature or trying to make something work within the features I have. And this is a thing where I decided, you know, 8 isn't a very big number. I can survive making it work within these features for now. But there might be an argument to be made that I'll be giving up a little bit of performance because of this, and if I had represented it as a real counter, I could smoosh this all the way down to one state and just add the idea of counters the same way I added idea of flags to a state machine. But then I'm using the counter just for this one specific thing, and so having a special case seems worse to me. If I had a couple counters in different places, then it would be different. And I do actually have one more counter right here, but it's also pretty small. It's like, yeah. Seems like a little bit of overkill to me for now to try to add counters to handle those. Let's see, yep. 234, you have, yeah, a lot of different things subtracted out here. So that's checking for octals. This is the base set of things that can be escaped, and these are other types of escapes. Here's the string thing, which we've already checked. And just gonna run through the rest of these, and I'm pretty happy with this. This looks like everything makes sense for the most part. Legal characters inside of it include delimiter and fallback. Legal characters inside of it include delimiter, fallback. Why are these separate states instead of a flag? Just thought that made more sense in this particular case. Usually I don't use a flag to pass one piece of information. A flag is for carrying information over multiple states, where if I can just say, hey, this is going to cause a split, but it's a split in a leaf state that basically that state will never do anything besides go to root, or like in this case go back to itself. That's simple. If that state is going to be a thing that can lead to 20 other possible states before it goes back to root, that's, you know, 20 things I have to copy, so then a flag makes more sense. Okay, yep, makes sense. Here's a thunk. Another thunk. Yeah, it's a lot of interesting optimizations for us to apply here. Yeah, that's fine, that's fine, that's fine. F number exponent. Yeah, that's about right. 5, 6, 7, 9. 0, 1, 2, 3, 4, 5, 6, 7, 9 is a bit of a weird set of numbers, don't you think? Why would F number decimal not allow 8. Seems like that's just a typo or something, right? I mean, surely this should not allow 8 because it's the octal. But these are not octal, these are just floating point number parsers. So there I have 8 and 9 are legal as an identifier. Operator or F number dot. So I've seen a dot. If I see any digit, including 8, that makes sense. I'm parsing a number. It doesn't matter. I already know that it's a number. So I already know that it's not octal, or I would have been in the octal case by now. So 8's allowed. Here I know I'm parsing a Z number, so if I see anything after the 0 that looks like an octal digit, I go to the octal case. So that 8 and 9 aren't allowed to transition me into the octal case. Here I already know I'm parsing a decimal for a floating point, so 8 and 9 make sense. Exponents can have 8s and 9s in them. Exponent signs can transition to 8s and 9s for exponent digits. Exponent digits can have 8s and 9s in them. 8 is allowed in a hex. 8 is not allowed in an octal. It's allowed in a PP directive. It's allowed in an include plenty and include quotes. Not in an octal. It's not allowed in an octal. Not allowed in an octal. It is allowed in hexadecimals. There we go. Okay, so that is a nice thing to have caught. Moving on. Fallback. 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 Alright, so this has a fallback, but it turns out that it's smaller than some of its primary handlers. These two are actually consuming identifier characters, and since all of the non-ASCII, like all of the characters above the ASCII range are considered legal in an identifier in my Lexer, so that you can have UTF-8 identifiers, turns out that my fallback is actually smaller than something else in the set, or in the like list of transition handler cases. And this, I believe we're at the root now, so its fallback is the smallest fallback of all because it handles almost every character with the exception of like 31 of the 32 characters at the beginning of the ASCII range, I think. I think these 31 characters represent like the delete character, probably the @ sign, and the backtick, and then all of the characters in the 0 to 31 range, except for new line, carriage return, the white space characters, basically, right? So the non-white space characters in that range, plus the 3 that aren't in C++, @ backtick, and finally the delete character at the end of the ASCII range, are those 31 right there. Does that make sense? There's 6, so in the first 31 in the first 32 characters, there are 6 white space characters. So you would actually need to make up 1, 2, 3, 4, 5, 6. So you'd have to make up, to get to 31, you'd have to make up 5 of them. Right? No, the count is 31. And here, if I look at 0 through space, makes up 33 characters. Right, so 33 minus the 6 white space gives you 27. You add back in delete, backtick, and the @ sign. What am I missing? There's one other character somewhere that isn't legal. Maybe backslash. I don't think... No, backslash is allowed at root right here. Some character is not allowed from root. I don't know what it is. Here's our white space. All of those... I don't know what character I'm missing here. So some character that isn't allowed to be the beginning of a token but is legal that I'm not thinking of? Six white spaces. Delete is not in there. @ is not in there. Backtick is not in there. So there's 3 of them. There are 28 others to come up to make up for. I have 33 here minus the 6 white space characters is 27. So there's one other character. What are you? One other character. I don't know. I kind of want to see with my own eyes. Oh, is that the end of file? No, because the end of file actually gets a handler right here. Yeah, I want to take a look. I'm just curious. That might not be wrong. It'd just be neat to know. So, yeah, we can just run here. The first thing we get should be the root state. Right? Was your pretty name root? Okay. Your last transition should be your fallback. And let's look at your condition. So your condition set says no matter what the flags are, I'm sure that's what it says, right? No matter what the flags are, see any of these 257 inputs. Okay. What happens after you've had a chance to simplify? Now your last says any of these 31 inputs. What are those 31 inputs? That's what I want to know. Everyone's dying to find out what 31 inputs causes an immediate Lexer error to be emitted. So 0, 1, 2, 3, 4, 5, 6, 7, 8. 9 and 10 are white space. 11 is white space, 12 is white space, 13 is white space, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29, 30. So those yeah, those are all ASCII characters that don't actually mean anything for the purpose of lexing. So then, what are these other ones? 96 is the character backtick. 64 is the character @. 59 is the character semicolon. Okay, so that's a bug. Good thing we took a look. How could I be missing a semicolon? So I'm guessing the root state itself won't actually have a semicolon handler built in. Right? So there's no obviously apparent place where I talk about semicolon. But I thought the opset would have this. Main ops. Main ops? I don't have semicolon in here. Okay, good catch. Kind of a big deal to have a semicolon handler. So there we go. Now it's down to 30. Alright. So there's there's some good progress. We've got the we now know that our set code is properly functioning, or at least we're fairly confident that it is based on the inspection we've done. And we know that our simplified transitions is properly functioning on top of that. And we added this new ability, this cool ability to print out the results of the simplification that we've done so far. And finally, what I want to do is I want to end on making some notes. As we were examining this, we got some new ideas about simplifications we should add to the system. So here's what I want to do. Before we optimize all action lists that don't contain a consume action, I want to add optimize all thunk states out of the machine. So a thunk state was that stuff we were talking about down here and a few other places where no matter what it sees, there's the transition is always do this work no matter what you see, and there is no consume. So essentially a thunk state does some action that could just be moved to the action list of whoever transitioned into this state, and then take the destination this goes to and put it over them, and then take that state out, right, of the system. So, yeah. That will be a cool thing to do first, because we can get rid of thunk states and look at the result right away, and that'll be pretty easy. And then we can take a look at, one more thing I'll do before we call it done is when we do this print transitions, I want to add in one more thing, which is at the top before we do this, I want to print out the number of states, so that we can see that number go down as we continue to optimize the system. Could kind of be cool to see if we actually optimize out any states already. I don't think we do. I don't think simplify states call should catch anything for my Lexer as I've defined it, but that's not to say it wouldn't ever catch anything for anyone. It's just I don't think it does in my case. But still, it'll be cool to see where we're at and see how it changes as we work on these optimizations. Something I should have done earlier on in the project, actually, but I was a little caught up playing around with the set math to think about some of these other details. So, yeah, we can just look at the count on the state set, I think. Yeah. Call that. We have 76 states. So just for funsies, I want to see what happens if I do this here before I simplify anything. Still 76 states, but now you'll see things like here our fallback says it has 257 possible inputs that trigger it, and we've learned actually that it's 30 once we do all the set subtracts to shrink it down, right? And this is it was also kind of cool to see that even after like all these complicated flags get involved, it turns out that they all just cancel each other out, and this ends up with a very simple all-stars flag pin with no chaining or anything, right? We can see there's also like plenty of other places where simplifying the transitions, there will probably be places where we see more than one fallback stacked up in a way that looks very different. Let me come down here to the bottom. Where I think we'll see some of this. 256. How are we getting? Oh, I'll have to, if I want to find it, I'll have to take this one out because this is the simplified one that we're looking at the bottom. So yeah, here you can see there's like these 257s that are like really weird looking. So for instance, here we have an op stage that says here's what I do, and then it happens to also say I do this and this, and that gets removed. Now that might be a bug. I'm not sure why it would say that it has this first and then also this and this. There's like several of those, right? This also thinks that it does something on equals, but that gets added after it's already determined that it always does this. So I don't know. We should take a look at that. That could be an actual bug that we should look at next time before we move ahead on anything else. But you can see that even if the construction of this is incorrect and there shouldn't be this here, it's also the case that our transition simplifier took all of this stuff out, right? So if I switch it over and say, let's look at this one. Now when we go to the bottom, none of these have redundant transition fallback things that overlap each other at all, right? So pretty cool. Alrighty, so that was this episode. I'll see you guys again on the next one, where we will look at that thing I just discovered, this suspicious construction of the operator parser, where we have a fallback and then an equal catcher and another fallback. Seems strange. Let's take a look at that next time. Bye.